Today's book is a sequel to the 1992 title, Predictions, which provided a new way of understanding society and ourselves by applying scientific concepts to predicting social phenomena. In addition to confronting the predictions made 20 years ago with actual data, something most futurists and forecasters generally avoid, today's book includes many new topics that became relevant more recently. When our guest was 18, he won a scholarship to study in the US away from his home in Greece. With a master's in electrical engineering and a PhD in physics from Columbia University in New York, he researched particle physics experiments at Brookhaven National Laboratory and afterwards at CERN in Europe. Later, he switched to the industry and worked at Digital Equipment Corporation as head of Management Science Consultants Group. 10 years later, he founded his own consultancy, Growth Dynamics, in Geneva. He is the author of more than 100 articles in scientific and business journals and 9 books translated into several languages. As an aside, he also applied to the Guinness Book of Records for applying the most data to S-curves. He has taught at Columbia University, the University of Geneva, INSEAD and IMD, and today we launch a series on a selection of his titles and articles, starting with the updated version of that 1992 book. We welcome the author of An S-Shaped Adventure, Predictions 20 Years Later, Theodore Modus. Welcome to the show.
Thank you for inviting me.
It's great to have you, man. I said to you, I wish I discovered this guy years ago because like you, I'm a fan of the S-curve and I learned so much. And once you have that lens of the S-curve, you see it everywhere. Let's share firstly your background, because you wrote again that 1992 book. You wrote it again in 2002 and produced a second edition of Predictions 10 years later, and then again in 2012 you wrote another.
My son told me, you should have one 30 years later. Oh, I said, come on, that's enough.
Well, people have used your data, including the great Ray Kurzweil, who used your data in an exponential curve, etc. So we'll get into all that. But I thought that we'd give a little bit of background to the book, and also that polymathic background you have. You have a wide range of different experiences, and that also gives a unique way of seeing the world.
Well, as you said, I was at CERN for quite a while, for over 11 years. And then came the crunch that I couldn't stay at CERN permanently, and we could no longer go to Greece as we originally planned for, because we'd been living in Geneva now for 10 years, and the children were growing up, and going back to Greece seemed too complicated. So I looked around for a job, any job, and I saw Digital Equipment Corporation at the time. It was at its heytime. It was IBM was shivering with fear because of what digital was doing. I wanted to talk to an old physicist that I knew from CERN, who had already a little group there, and he told me, "Come with us." He says, "We'll do science. We don't do computers." And he says, I'll let you do whatever you want, he says, as long as may help the company in some way, free hand. It sounded exciting. And then, in fact, he said, here, take this literature and read to see how intellectually astute we are. And he gave me the literature of Marchetti, some of the papers of Marchetti, Cesare Marchetti, from IASA. He was working at IASA at the time. And he's, the one of the promoters of this S-curve business. And by reading more and more of his stuff, I got so excited. I went back to my boss and says, "Look, I want to do the stuff." Yeah, he says, "But we should also do something for the company." But it was too late. I was taking so much with that. So my boss told me, "Look, if you're so excited, go to Vienna and talk to this guy." So I call up Marchetti and say, "Look, I'd like to come and talk to you." "Yeah," he says, "we can do that, but I'm leaving for Japan. Tomorrow is the only chance. Can you be here tomorrow morning by 8? I say, "Well, I don't know. I mean, accustomed to the way physicists do things at CERN and other big institutions, the University of Geneva, you have to apply for a trip 2 weeks ahead of time. So in the afternoon to go the next day in the morning in IASA seemed to be impossible. But when I talked to the secretary in digital, I said, is this possible? Let me check, she says. Yes, you have a plane tomorrow morning at 7. So I went to Marchetti the next day. We spent all day together. She gave me all kinds of information. And on the way back, I was so excited. It was clear that was going to become a new line of activity for me. And that's what happened. A year later, I was starting my first book, Predictions. And that was a big adventure. It was such an adventure that several years later, I wrote another book on how I wrote the first book, because the first book involved so many twists and turns and so much luck, but perseverance and highlights like Simon & Schuster, big deals, Nobel Prize winners, and the big dream of becoming a bestseller. You know, the Simon & Schuster bought this for me as a bestseller. It says, we expect this to become a bestseller. So all this fed up to my ego. In the end, I was hoping for a bestseller. In fact, the little book I wrote many years later is called Bestseller Driven, because it was all I did in order for my first book to become a bestseller. Well, I'm not going to tell you the story of the second book now, even though many people are asking me, that's one of the reasons I wrote it. Many people are asking me, how does one write a book? What do I have to do? And I said, well, there's a lot of things you have to do, but it's not easy for me to describe. It's a whole book on how to write a book, how to write a book that aspires to become a bestseller. I mean, anybody can write a book, but I wrote a book that from the beginning, it was groomed to become a bestseller. Well, it didn't become such a bestseller. It became a good seller, but Simon & Schuster was disappointed because they gave me such a big advance that they hardly recovered all the money they gave me. I had a very good agent, I must say. That's where the luck comes in, because it's not enough to have the material and everything. You have to have some luck. Without some luck, it's hopeless.
Well, as they say, Theodore, the harder you work, the luckier you get as well.
Exactly. I wrote a little book that says "Fortune favors the bold," but I published it a couple of years ago. So that's true. Yeah, luck helps the persevering. But anyway, so then with this background, I applied it to so many things that when I left the digital 10 years later, I have an 11-year cycle. My kid told me, oh, that's the sunspot cycle. What sign are you? I said, I'm Leo. Oh, voila, I said, that's the sun. I mean, you have a cycle. So after 11 years at digital, then digital had a hard time. It was bought by Compaq, and they were cutting out all superfluous stuff. And needless to say, this idea, go study anything you want, was not valid anymore. And I wasn't ready to get out and sell computers. So I quit, and I was ready to launch my own company on all the material, all the tools I had acquired. And so I kept doing what I liked doing in a scaled down situation, because I was from home now and I wasn't having my fat salary coming every month. But needless to say, I was just as happier for that matter.
It's so true, isn't it, with people who are driven by change and interested by change and curious, that when you do pursue your dreams, you're happier. Even you might not have as many luxuries, but that kind of force of the unhappiness working in a company that makes you sit at your desk and bureaucracy and administration versus you can pursue what you want to do. It's a much better pursuit.
I was spoiled. In fact, the first years in digital spoiled me, because, you know, when my boss there said, go and study anything you want, I picked it up and I liked it, and I couldn't give it up at the end. So I left, and I tried to find clients but again, along the lines I like to do, what I like to do, not anything the client wants to do.
It's very hard to go backwards, isn't it, after you have experienced
Oh,
that
it's
freedom?
hopeless. It's hopeless.
Yeah. So you mentioned, Theodore, some of the frameworks and tools that you picked up, because I found this most interesting, that everything I've read about innovation and change and S-curve, and I'm an S-curve user as myself, not a Guinness Book of Records S-curve user, but I'm certainly think that way. But what I found so interesting was, and why your predictions were so accurate and your forecasting was so accurate, is that you differ from other people in what you use, because yours relies on natural laws, and that's one of the books we're going to cover, is this natural laws in favor of the decision maker. We're going to cover that in the future. But one of the laws in particular is the law of natural growth in competition, otherwise known as survival of the fittest or Darwinian competition, because this you use with the S-curve. And this is why you see that kind of balancing out, or that decline phase at the top of the S-curve. For example, you give an example of rabbits, for example, competing for grass. I'd love you to give a helicopter view of the S-curve combined with this natural law of competition.
The fundamental law is a simple equation. I don't want to talk in derivatives and stuff that people may not be familiar with, but in words, it says the rate of growth is proportional to how much growth has already been achieved, but at the same time is proportional to how much growth remains to be achieved. So infinite growth cannot happen. You are growing, whatever is growing has a space to grow into, a niche to grow into. The amount of growth cannot be infinite. So the rate of growth is proportional to how much growth is achieved and how much growth remains to be achieved. This is a differential equation. You know, dx dt is equal to x times capacity minus x. So and that you solve this equation, you get an S-curve. So the S-curve is nothing but the mathematical and pictorial representation of this natural law that says that things grow according to how much they've grown already, but according to how much they are allowed to grow in the environment where they're growing, because it must be finite at the end. So the trick of this equation is the beginnings at the end become very difficult, because at the very beginning, when there's zero growth, the rate of growth is zero. So you have a hard time starting. How do you start something if it's proportional to how much there is already? If there's zero already, the rate of growth is zero. So philosophically, that's where an outside source is necessary, whether it's God or whether it's luck or whether it's something. In the beginning, you need something other than the equation, otherwise you cannot start it. And at the end, of course, it gets smaller and smaller, because the remaining growth gets smaller and smaller, and the rate of growth has to drop to zero at the end, because you filled up your niche. You exhausted what was genetically attributed to you as a capacity for growth. So the rate of growth is bell-shaped, because it starts from zero, it ends with zero, and it's maximum in the middle. The cumulative growth, how much you've grown, is S-shaped. So S-shaped and bell-shaped are, one is the rate of growth of the other, derivative in mathematical terms. The life cycle goes up and down, is the derivative of the learning curve. The learning curve is the S-shaped. And the middle of the S-curve is the peak of the maximum rate of growth. Things are growing fastest when the growth process is in the middle, when it's fully mature. In the beginning, it's growing fast, the rate of growth, and then it slows down and reaches the maximum, and then it declines the rate of growth. And the maximum is the middle of the process. To talk in terms of seasons, that's a summer season, when things are when they were at its best, on the fastest rate of growth, in the middle of maturity, and everything is rosy.
I'm going to share on the screen a graph from the book that you've kindly let me share. So those people who are watching us on YouTube, I highly recommend watching this. The book is full of these brilliant graphs mapping everything from the difference in horse utilization versus when the car came online, accidents, disease rates, and even back in 1995 when Theodore first gathered data for the curve, he unwittingly contributed to the then emergent singularity movement that we've seen absolutely flourish in recent years as well. But the reason I share all that is that you share the primordial growth curve that describes how change and complexity appeared in the universe from the very beginning, the Big Bang to today and beyond. Maybe you'll say a word about that, and I'll share this diagram on the screen.
The curve you see on the top, the S curve, so to speak, is the population of the ecological niche. The pair of rabbits on a fenced-off grass field. The two will have 4, the 4 will have 8, the 8 is 16. They multiply exponentially. So in the beginning, the population grows exponentially. But to the extent that the population grows so big that there isn't enough grass around, remember, it's a fenced-off grass field. So there isn't enough grass to feed all these rabbits, then the population will slow down. The growth of the population will slow down. The size, because some rabbits will start not having enough food. The more aggressive rabbits will eat the grass first, and the most weak rabbits will die. In fact, the rabbits may overshoot the capacity. Here is the gray line. The population may get bigger than the capacity, and they're not going to have enough to eat, so they're going to start dying. And if enough rabbits die, the grass will get a chance to grow again, and the rabbits will grow again. So you have this kind of oscillation over there. We call it a homeostatic equilibrium at the top of the S curve, which means that you have filled the niche, the ecological niche has been filled. Now, the rate of growth, it's how many rabbits get born per month or per week or whatever. In the beginning, it grows just like the size, exponentially in the beginning. But then to the extent that you start feeling the squeeze of the food that becomes more and more scarce, the becomes less, and the rate of growth declines. And at the very end, when you reach capacity, the rate of growth goes to 0. So there's no more growth of the population when the ecological niche is full. That's the mechanics around the S curve and its life cycle.
I'd love you to apply that same model, that same frame to organizations, because it's the similar thing. You're competing for customers.
If there is any difference, it's the fact that organizations are likely to mutate easier than species. Species also mutate under stress, and even without stress, accidentally they mutate. You have to be careful about that. You have a nice curve for an organization, and all of a sudden it goes berserk because the CEO was replaced with another CEO that had a completely different ideas, and effectively the species became a different species and cannot follow the same curve anymore. So you have to watch out for this kind of phenomena.
And one of the things that dawned on me was, you mentioned there, you need an outside force. So if you're at the top of that curve, the outside force is you need to be investing in the future. You need people like you back in DEC going and looking for new opportunities, new grass to feed on.
Take risks, explore different directions. In a desperate situation, you try all kinds of things until something works, and a new seed gets in the ground, gets a chance to grow again. But it has to be different than the old one. I mean, you put the same old seed, it's not going to grow.
Extending the analogy a little bit more, you also need to fertilize the ground and keep it, look after it, pick the weeds.
Help it along. There's no question.
I love when you talked about the proverbs like easy come, easy go, early ripe, early rot. When it rains, it pours. You need money to make money. All beginnings are difficult. You kind of go, oh yeah, that's really what those things mean if you apply them to the S-curve. But speaking of which, I mentioned all the different applications you used for it. And I'm going to share on the screen now one of the graphs that you share, which is the example of car accidents. And you observed that deaths by car accident grew along an S-curve with the appearance of cars until the mid-1920s, when they reached about 24 per 100,000 per year. And then they stabilized from then onwards. I thought this was really interesting because it shows the homeostatic mechanism that you mentioned there, where the limit is reached. So I'm going to share this on the screen, and I'd love you to talk to this one.
Cars came into the early 19th century in a big scale, and the numbers kept growing, and the accidents also kept growing. But that wasn't important until the accident rate reached a threshold. It appears that society can tolerate a certain number of accidents, but not more than that. So how this level is decided is not clear. But apparently, when you got more than 25 deaths per 100,000 population per year, society reacted, and legislator was put in place, and cars became more safe. Safety regulations tightened up, and so for the next 50 years, we see an auto-regulation process where society reacts and technology advances, and people and more cars get on the road, and more they go faster and faster. More and more roads are built, but the number of deaths per remains constant because society doesn't tolerate big. This is the price society is willing to pay for the use of cars. In fact, there's a similar price, the similar curve I have done recently for the use of guns. It's about half as much. It's about 12. 12 deaths per year due to guns is how much society tolerates. And then when that goes up, gun laws become more strict. But no one person is responsible for this auto-regulation. In fact, not even governments are not responsible. It's a bottom-up effect. Society itself reacts through legislators, through public opinion, through publications, through the noise, through the media. When accidents get over here, for example, in the early 60s, remember, you can see how the number reached about 27 from the 23, which is the homeostatic level, it went to 27. Well, that excursion was too much. So at that time, there was a big push against cars. Ralph Nader's famous book, Unsafe at Any Speed, became a bestseller at this time here. Everybody was talking about cars being murderous weapons. And all this had as a reaction to make seatbelts obligatory, tighten safety, put safety features in cars, tighten the laws, and the number came down again. So people stopped talking about cars and start talking about pollution or other things. But so this is the auto-regulation I'm talking about, that no single person does it. If Ralph Nader didn't do it, somebody else would have done it, or the public opinion would have reacted with too many car deaths.
I thought about how you were saying that. I was like kind of going, next time I'm going to write a book, I'm going to actually talk to you and go, what's coming down the line, Theodore? And write a book and be the Ralph Nader and create a book for the actual need that's in society. I wanted to share something based on something that you said. We spoke recently on the show about homeostasis in a series about the brain with Mark Soames, and I thought it was a great metaphor for organizational change, that when the organization gets out of homeostasis, there needs to be an outside force to get it back to equilibrium again. And it links to something you wrote here, because I thought this was brilliant. You said, fatal car accidents exemplify the concept of an invariant, which does not change over time and locations. And I'd love you to share this. You say, invariants are, of course, the easiest thing to forecast. They reflect states of equilibrium maintained by natural regulating systems. They often are the ceiling of an S-curve. In ecosystems such equilibriums are called homeostasis and refer to the harmonious coexistence of predator and prey in a world where species generally do not become extinct for natural lessons. I'd love you to unpack that maybe through the lens of an organization, or how this manifests in competition in a business environment.
When you reach the top of an S-curve, theoretically it's flat, but in practice it's oscillating up and down around this level. So the excursions, upward excursions and downward excursions, and they average on this level. the bigger the excursion, the more the restoring force will be. Whether the restoring force comes from law or from public opinion, or whether it goes underneath and neglected, you just attention shifts elsewhere. So this variable drifts upwards again because nobody controls it anymore. So the equilibrium of the top of the S curve is bottom up. You see it there and you adapt to it, because every time you go to excursion, either upwards or downwards. Upwards you feel the pressure, downward you feel the oblivion, you forget about it, and it just sprouts on its own. So what counts is that you remain on this equilibrium level.
When you mentioned there oblivion, so you're on your way down, is that where you forget, you've lost your competitive edge?
What I meant oblivion in the sense that the accidents go down and people forget about paying attention to the car safety. The speed limits drift upwards. I mean, in Arkansas had no speed limits for a while, because there was exactly the period where the number of deaths per car accident was way below the 25 canonical, let's say, level. And then they experimented with no speed limits at all. Now, that didn't last very long, because when the number crept up again, the number of deaths per 100,000 per year due to car accidents, when that crept up again, the laws came back in. So that's the auto-regulation I'm talking about.
It shows why you never let a good crisis go to waste.
Yeah, crises are cause for concern, cause for restoring something that has gone wrong. That's what I see a crisis as a restoration force.
One last thing before I go on, because I wanted to get into a little bit more fascinating things about invariants, but I'd love you to give maybe a high-level definition of what an invariant is before we move on.
Invariant, as the word says, is something that doesn't change. It doesn't change over time. It doesn't change over variables that may, the weather changes, but that doesn't change. The sex, the authors change, but invariant is just something that remains the same over time, without really necessarily understanding how that happened. Hence the numbers.
The number of deaths, for example, that's an invariant. You know, it's kind of stable.
The number of accidents. I mean, the top of the S curve in accidents that we saw before, 25 deaths per 100,000. That's an invariant. You know, invariant. It keeps oscillating, goes up and down, but the long-term trend is invariant.
Brilliant.
Invariants are theoretical, and you cannot have something flat in reality. But what you do have is fluctuations around a flat trend.
Speaking of trends, one of the amazing ones, this one blew my mind. You wrote in Predictions, you discussed many invariants in social situations, and one of the ones that I found absolutely fascinating, particularly after we all experienced lockdown, was that humans worldwide are happiest when they are on the move for an average of about 70 minutes daily. And you wrote here, this is mind-blowing. During these 70 minutes of travel time, people like to spend around 15% of their income on the means of travel. And that actually follows somebody's wealth patterns as they grow older. I'd love you to share this.
And within this 70 minutes and 15% of income, they want to reach as far as possible, to go as far as possible. So the spreading, they have to cover a bigger and bigger area. Yeah, these are the so-called invariants, and they have their roots deeply into the nature of human life and behavior. And they typically represent the top of an S curve, because something had reached its optimum volume. Optimum in the sense that if it goes above, there's pain, or if it goes below, there's negligence, and it drifts up again, because if if it goes below, you are neglecting it basically in favor of other things which may impact the rise of what you're neglecting.
And this made sense to me where you were talking about this idea of maximizing range. And you say, after all, that's what all living organisms are trying to achieve, from the most primitive ones to humans. The rapid multiplication of unicellular amoebas and space exploration aim to expand into space as far as possible. Or as Marchetti put it, every other rationalization tends to be poetry. I love that.
He's my mentor, he died, the poor guy, last year. So that's true. I've been thinking about this. I'm not even thinking, it has become a second nature to me now, this idea that expanding in space is natural, and you'd have to do it according to respecting this invariance, respecting the law that says in cars that you shouldn't go more than 25 accidents per 100,000 kilometers, deadly accidents, and generally the homeostatic level is an equilibrium position which is optimized, which is bottom-up optimized. Nobody has optimized this consciously. It has been optimized by nature, and society has decided this level of 25 deaths per 100,000 inhabitants, but nobody has dictated it. Nobody has put it there.
I often think about that, Theodore, even like you working in DEC, that just the same happens in nature. So, for example, in bee populations, there's always an ants, for example, really sophisticated animals. There is always a portion of the population who are explorers and looking for more. And then there's always the worker ants and those people, the worker bees, who do the work all the time. And I thought that's exactly what happens in organizations with change makers like you were in DEC.
Typically with DEC, they had told me, study anything you want as long as it can help the company in some way. This was the heyday. They had enough revenue to afford this. But they also realized that this is useful. And this is something that promotes the survival of the company.
And that's the outside force again, isn't it? That the outside force, which was you, bringing new information. There's a new pasture over this way. There's new grasslands.
I wasn't one of the traditional members of the company. I wasn't thinking in the same way. I was a physicist. In fact, I had no particular interest in computers other than using them in the way I liked. And on the other hand, I was very much interested in the physics and the fundamental ideas. And they wanted to apply them towards a competition with other companies. And I said, okay, well, if it's competition, we know how it works.
Brilliant. I love that. And I love the fact that they did that. And unfortunately, like you experienced, as soon as the organization becomes under pressure at the top of the S-curve, the first people to go are the explorers, the curious ones, unfortunately.
I think DEC had a short life cycle because it went up too fast. The life cycle is basically symmetric. The old saying, easy come, easy go, it came up very fast, and then it came down also fast, while IBM has a life cycle that goes like this, so that it takes very long time to grow, and it will take very long time to decline. Probably will mutate before it declines completely. But with digital, it was very fast, and that's why, consequently, it was also very exciting, because fast change is drive you, it's intoxicating. It's very exciting. I mean, I remember I studied Marchetti's ideas for a while, and then I went to the business school, IMD in Geneva. I had a friend there. I presented him the idea. I said, look, do you think that this is worth teaching in the university? And after a while, he told me, why do you want to teach? This thing is so exciting. Go write a book, write a bestseller. I mean, go do your own stuff. You go to teach, you just become a teacher, he said.
Something you said there is so important. That idea of easy come, easy go, or the quicker you grow, the quicker you'll die. I like, the more I read, and I'd love your thoughts on this. Like the books I read eclectically, as you know, and you do too. And I find actually, when you do that, you discover these universal laws. You discover these universal frameworks that work for everything. And something you said there, like I looked into nature. So a mouse grows, reproduces really, really quickly, but a whale, which lasts a lot longer, doesn't get so much disease. They grow much slower, and therefore they live longer. And I think there's huge wisdom in that when you think about it from an organization perspective, even from an investing in a company perspective. You gotta go for slow growth. You can't push it. There's a natural growth curve that has to be obeyed.
That's right. In fact, we have a publication with a mathematician friend of mine, digital. He was helping me with the math that describes just that. How much can you slow the growth artificially in order to increase the size you will become at the end? Because easy come, easy go. You go very fast, you will decline very fast. Alors, very slow growth may last very long, but you will never become very big because it's so slow growth. So we're trying to find the optimum of how it is to grow fast enough, but not too fast. In fact, we did publish an article on these issues with how to estimate the optimum S-curve or the possible S-curve, the most likely S-curve that fits a number of data. So that there is predictability. It's not magical. It's not like you will tell you the future in some kind of a magical way, but you will know more precisely how much can be done and with what probability. So all this is quantified. This is a publication we did many years ago, and it has lookup tables like given how many points do we have, and what's the accuracy per point, and how much confidence level we want to have on the answer. You put all this inside, and it gives you a number. It says 80%, for this kind of thing you're asking for.
It even applies to stuff like muscle growth. So if you try and cheat the system and take steroids to grow muscle, the tendons don't grow, and then the muscle actually tears. Or the same with, it's called rank growth in plants. If you feed the plants and they grow too quickly, they don't grow that stress wood on the inside of the plant, so then they just tumble over and they become kind of floppy.
It echoes the golden mean, some kind of a ancient knowledge of a golden mean. But you do it mathematically. You do it rigorously and precisely.
And I'm going to link in the notes to Theodore on YouTube, where he shows how to use Excel to use the S-curve as well. So we're going to link to that, Theodore, for people.
Okay, yeah.
We've covered the natural growth curve, the S-curve, the primordial growth curve. We've covered invariants. There's another term that's interesting and needs to be understood, which is deviations. And here you say unnatural events such as a world war, major earthquakes, natural or economic catastrophes, and any other singular but significant phenomenon that never occurred before during the historical window under a study may introduce short-term deviations from the S-curve trend. But here's the interesting thing. A return to the S-curve course is expected when the unnatural event subsides. Other deviations from S-curves, you tell us, may involve simple fluctuations such as phenomena as cascading S-curves, the early catching up effect, the final overshoot, a niche within a niche, and a niche with a variable capacity.
As always, with science, there are complications, but just because life is complicated, and you never have only one species like on a niche. You have more than one species. You have interactions which may differ than predator-prey. You may have like the grass and the rabbits. It's a predator-prey relationship. The rabbits eat the grass, but you may have rabbits and sheep, which is not predator-prey. One doesn't eat the other, but they both eat the grass, which serves for food to the other. And so there you have a different type of relationship. And in my book, Conquering Uncertainty, I analyze this kind of competition where you may have plus, 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 minus, minus, plus, minus, minus. If you have two species, they can interact in that different ways. One can influence positively the other, symbiotic. One can influence negatively the other, predator-prey. One can positive, positive. No, negative, negative is the classical antagonistic relationship. And commensalism occurs in a parasitic type of relationship in which one species benefits from the existence of the other, but the other remains unaffected. So you have 0 plus. One species benefits and the other one is impervious to what the one does. And amensalism, this is the most exotic one, is -0. That is, one species suffers from the existence of the other, but the other is impervious to what's happening. So all those four are possible, and I give examples of these.
It'd be fascinating to map them to the type of competition in a business environment.
Exactly, but that's what this book, Conquering Uncertainty, is a business book in principle, in a popular style, because whenever I write, I want to have a bigger audience. So I never write only for the business person, but in this style, I'm addressing a business problem, which is competition. And there are different types of competition, plus, 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 minus, 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 plus, all the combinations. And
oh man, we're going to have to get that in as well into the series. We'll never be finished.
well, okay.
No, with pleasure.
No, you decide. Well, make a choice and pick up whatever it's interesting to you, and let's stick on that, because I've written many books, and in fact they're old one now. I have to go back and remember what I said. As I say, so I spent yesterday all day trying to remember what the book really contains, because I have moved on, and I'm excited about other things.
I thought we'd show a couple of deviations and show some of the work that you did back in Predictions. For example, in Predictions, you contrast Mozart's textbook's S-curve to Schumann's curve that was punctuated by deviations such as a nervous breakdown. I'll show that on the screen again because it's absolutely fascinating, and maybe you'll share this because I really want our audience to understand how the S-curve can be applied to any phenomenon.
Well, here is Schumann's collective compositions throughout his lifetime, and we see that they roughly follow an S-curve. Everybody has an S-curve in creativity. That is, in the beginning, you cannot create very much. At the end, you get tired and you cannot create very much, and you're mostly creative in your active part of your life, in the midlife. But if you have a turbulent life like Schumann, who had problems, he had a nervous breakdown, he committed suicide, he attempted to commit suicide, he committed suicide at the end. So these things are not natural, and in a way, they interfere with the natural evolution of one's work, which should follow an S-curve, because what can be more natural than an S-curve evolution? So we see here Schumann's compositions, and we see a nice S-curve in the beginning, which deviates from the final one a little bit, because it's punctuated with a nervous breakdown, which slowed it down. But then it picked up again, and it's punctuated again with his attempted suicide. He stopped for a while, and then even died, but his compositions kept published by his wife or his friends later on in a curve that continued in a third. So there are three curves, successive S-curves here, punctuated by different important events that took place in his lifetime.
Theodore, I just want to understand. So each of those, they're jumps to a different curve.
There are three S curves cascading. In the overall pattern of an overall S curve, but they are smaller S curves which are describing what was happening in that period, the period of the youth, the period of the breakdown, the period of the post-mortal, because his publications came post-mortal. There was a whole S curve of publications after his death. His wife and followers just made sure that his work becomes known. But of course, his death did disturb the evolution of the appearance of his publications in public.
As a special treat, this is not in the book. This was edited out from the version I have from the 20 years later. Theodore has the Mozart curve. So this one's fascinating. Over to you, Theodore.
What we see is the cumulative number of compositions Mozart made. They start, the first one is when Mozart was 6 years old, and the cumulative number grows along an S curve, of course. It was a natural growth. And it stops, it reaches 93% of its ceiling when Mozart dies. So it's almost a natural death, because if you're above 90% of your potential, you really accomplished what you came on this world for. It's interesting that the last year, the last point is above the curve. If you saw the movie, whoever saw the movie, remember that Mozart was composing on his deathbed, frantically composing, sick, because he knew, he felt that he was not going to survive. And he wanted to complete his work as much as possible. You know, the last point brings him to 94% of the potential. So he's more accomplished, so he can die more easily. But his overcomposing during that last year in his deathbed is due to the fact that he probably felt he was going, and he wanted to complete his curve as much as possible. Now, on the other end, in the beginning, we see that the curve extrapolates to at zero, something below zero. It's 70-55. We don't get the beginning of the curve. In fact, you can never get the beginning of the curve. It's asymptotic to zero. But there is a significant, that is, if you take the life of Mozart at age zero, when he was born, there is a certain potential lost. There is about 6 or 7 compositions that have been lost in the very beginning, because he was composing from birth, but he couldn't talk, he couldn't write, he couldn't document his composition. The first composition is when he was 6. So during those 6 years, we have lost a number of compositions here, because a genius the way he was born as a composer from day zero.
That speaks to what you said about in the start, there's not enough energy to get the S-curve going, right?
Exactly. The beginning of it is complicated.
The beginning is always complicated. So I feel today's episode has reached the top of its own S-curve. So we're going to finish there. And Theodore was joking with me before the show where I said, we'll probably only get through chapter 1. We actually have only got through chapter 1 and we didn't even get near it. So we're going to move on to future episodes. Are going to include the limits of growth. And as you can see, I hope you're really learning from this, the fact that these tools can be used for any phenomena. And we're speaking to the expert, the person who has applied to the Guinness Book of Records for the amount of applications of data to an S-curve. And it's been an absolute pleasure. Theodore, for people like me who reached out to you to find copies of your book, because I did hunt some down on Amazon behind me here on the library, but also you do sell them yourself.
My company's website, growth-dynamics.com.
And I link to all the places to find Theodore, including his books and his articles. still publishing articles ongoing as well, like you mentioned during this episode about the guns. It's been an absolute pleasure speaking to you, author of An S-Shaped Adventure, Predictions 20 Years Later. We'll look forward to 30 years later. Theodore Modus, thank you for joining us.
Thank you. Thank you. Have a nice day.